Welcome back and welcome to Unit 3. In this unit what we're going to be doing is we're going to be exploring the concepts involved with applying the derivatives. A lot of times finding the derivatives, simplifying the derivatives, and solving the derivatives are the hardest parts of these problems. But in this first video we're going to explore the concept of related rates. And what related rates are is that when you have two or maybe more variables changing at the same time, and we can express them as a function of time. So we can take a look at like the change of the radius versus the change of the volume of a cone or a sphere, something like that. Then we set up that relationship between the variables and we solve the equations. In these problems you want to draw yourself a good picture. You want to write an equation relating to variables, Pythagorean theorem, geometry equations. You don't have to memorize any of the geometry equations. I'll give you all of those, so will the AP exam. Solve for any missing variables that you can. Differentiate with respect to time. So every time you take a derivative of a variable, like if you take a derivative of x, you got to multiply by dx dt. You're going to do it implicitly. Substitute in all the values you know, and then finally solve. Let's look at some examples. In our first one, I just have a nonsense equation. And in my nonsense equation, I'm just relating x and y, just to kind of get you used to the idea of taking the derivative in terms of x and y. So in this first one, the derivative is going to be 3x squared times dx dt minus 4y times dy dt plus 5 times dx dt, that's x dt, equals 0. And then plug in all the values that are given to you, 4, 2, negative 1 in different situations. So 3 times 2 squared times 4 minus 4 times negative 1 times dy dt, which is our variable, plus 5 times 4 equals 0. And then when I solve that, I get dy dt equals negative 17. In many of these cases, we're going to have units like feet per second or inches squared per second or something like that. But in this first one, we don't have any units and measures, so you just leave it that way. There's a lot of relationships that are based upon Pythagorean theorem, and we do this old-fashioned problem with a ladder leaning up against a building or leaning up against a wall. In this particular case, we have a vertical building. We have a 20-foot ladder, so this is 20 feet. And then we're going to take a look at these rates of change of these different variables when this ladder, when this x value is going to be, x is going to be 12 feet away. And that's consistent for all the different parts of the problem. And what's happening with the bottom of the ladder is the bottom of the ladder is being pulled away from the wall. So as the bottom ladder is pulling away from the wall, the x variable, dx dt, is changing, squeeze it in here, at 2, and that's 2 feet per second. And I'll do that as we take a look at this and I answer the question in a few moments. I'll put my units and measure on there. And then the ladder's coming down the wall, and when I get my answer for the ladder coming down the wall, this, I'm going to call this y variable. This is my y variable, and I want to know dy dt. And that y variable, when I solve it, it's going to be negative because that distance is getting shorter. That's important. You have to know that, like, when the distances are getting shorter, you always got to represent the rate of change as being negative. So the relationship between the variables is that it's Pythagorean theorem. So it's going to be x squared plus y squared equals z squared. The one I don't know right now is y. I can solve for that by plugging in 12 here and plugging in 20 here. And when I solve for y, I get y equals 16. It's a nice Pythagorean triple, 3, 4, 5 triangle that's multiplied by 4. And then I want to go back to this relationship right here, and I want to, that's the one I want to take the derivative of. And when I take the derivative of that, when I take the derivative of z, the 20-foot ladder, that's going to be 0 because 20 feet is a constant. It's not changing. So since it's not changing, that derivative is 0. So when I go to take this derivative, it's going to be 2x times dx dt plus 2y times dy dt equals 0. Plug in all the values you know. The 2's will cancel out. These you can drop out, divide them out. This is going to be, the x value is going to be 12. dx dt is going to be 2. It's getting larger. The y value we just found to be 16. The dy dt is my variable. And that equals 0. And when I solved that, I found that dy dt is negative 3 over 2, and that's feet per second. Okay, we're going to use that information for B and C. In the second part, we're looking at the triangle that's formed by the ladder, the wall, and the base, and we're looking at the change of the area of that relationship. So area is 1/2 of x times y in my drawing. When I take the derivative of that, all these variables are changing, so I have to use product rule. So a prime, or let's go back for a second. Let's not use a prime. Let's use dA dt. So dA dt is equal to 1/2. I've got to use product rule, so it's going to be dx dt times y plus dy dt times x. I have all those values, plug them in, so I get dA dt equals 1/2. dx dt is 2. Y is 16. dy dt I just found to be -3/2. And x is 12. And then when I solved that, I ended up with 7. And since it is a rate of change of area, these are all in feet per second in feet, so it's going to be 7 feet squared per second. It's the rate of change of an area, so it's always got to be units squared. And then finally, the last piece of the puzzle is I'm going to take a look at the rate of change with the ladder. The angle is changing between the ladder and the ground. So it's this little part right here. I'm going to call that theta right there. And so I'm going to use, in this particular case, because it's a right triangle, I'm going to use SOHCAHTOA. I'm going to use a sine relationship. And the reason I chose sine is because the 20 is not changing. So since the hypotenuse is not changing, I want to use sine or cosine because I want to use the hypotenuse. I would not use tangent. Tangent would be much harder. So if I use sine of theta equals my y value over my hypotenuse, which is 20. And since 20 is a constant, I can put 20 in there. It's not changing, so I'll have to take the derivative of it. When I take the derivative of this, it's going to be the cosine of theta times d theta dt equals 1 over 20 times dy dt. I know what the cosine of theta of this angle is. The cosine is my adjacent, which is 12, over my hypotenuse, which is 20. So it's going to be 12 over 20 times d theta dt equals the 1 over 20 times -3/2. These 20s will cancel. So d theta dt d theta dt is going to be equal to -1/8. It's going to be -3 over 24, which I reduced to -1/8. And then in this class, everything is in radians. So this is in radians per second. Always make sure you label those. Pythagorean theorem, two different types of problems. I'm going to do one in just a moment where everything is changing, and then we have to, when I take the derivative of it, it doesn't become 0. And then this one, like the ladder changing, the ladder's not changing, so therefore when we take the derivative of that, it is 0. Let's go to geometry. The first one's going to be a cone, and in this particular case, we have original height. This height is going to be 16, and this radius, that radius is going to be 8, and those are in feet. What I know is that the water is flowing into the tank, so the volume is getting larger, so dV dt is positive, it's going up. Is going to be 2 feet cubed per minute. And we want to know how fast the water level is rising when the height is 5 feet. One of the formulas that, you don't have to memorize these geometry formulas. The volume of a cone is 1/3 pi r squared h, and I'll give that to you on any test or quiz. In this particular example, what I'm looking for is I really am focused on what is the rate of change of the height. So I want to replace this r variable. I want to get rid of that. And the way I get rid of that is by developing this relationship between the original radius and the original height. This is going out gradually as it goes up. And so therefore, the radius, the ratio of the radius to the height of this particular cone is always going to be in the ratio of 8 over 16 or 1 over 2. If I solve that for r is always going to be 1/2 of the height. That's the way it's always going to be. It's only for this particular cone, not for all cones, but just this particular one. So I can rewrite the volume as 1/3 pi times 1/2 h squared times h. When I simplified that, I can write the volume as going to be pi over 12. It is going to be pi over 12 times h cubed. So now we have the volume all based upon the height. And when I go to take the derivative, then I'm just going to have a height is my variable. So my next step when I take the derivative, dv over dt, is going to be pi over 4 times h squared times dh over dt. I'm going to plug in my variables I know. This is 2, so 2 equals pi over 4 times 5 squared times dh dt. dh dt is what we're trying to find. And then finally, when I solve that, dh dt is going to be 8 over 25 pi. That's a pi. And that's going to be in feet per minute. It's a change of a linear measure, so it's feet. It's not feet squared. These are also a lot of calculator problems. See, if you have 0.102, that's fine as well. Round off everything to 3 decimal places. Let's head back to Pythagorean theorem. And in this one in Pythagorean theorem, we have these cars that are moving. They're moving towards the intersection. So one is moving south. That's the second guy. One is moving east. That's the first one. And when you do this, since the distances are getting shorter, the rates of change need to be negative. So this one, the x variable, he's 2 miles away. And dx dt, he's moving at negative 40 miles an hour. The reason why it's negative is because that distance is getting shorter. This guy at y, he's 1.5 miles away, and he's moving at dy dt negative 35 miles per hour. And we want to know the rate of change of z. We want to know dz dt. And the first thing I need to find is z when x is 2 and y is 1.5. Use Pythagorean theorem, you find this to be 2.5. Again, a 3, 4, 5 triangle, and we're just multiplying it by 0.5. And so then we set up this relationship, x squared plus y squared equals z squared. But unlike my previous example where I was doing with the ladder, when I take this derivative, all these variables are changing. So I got to keep them all. So it's going to be 2x times dx dt plus 2y times dy dt equals 2z times dz dt. The 2's will drop out. Plug in all the values that you know. Plug in all these numbers that you know for x and for y. And I solved it out, and I got dz dt to be negative 53 miles per hour. And that makes sense that it would be negative because this hypotenuse is getting shorter. As these cars go towards the intersection, this length is getting shorter, and that's why it's negative. One last example on a sphere. And with the sphere, what's going to happen in this one, you just got to be a little bit careful of units because I give you the diameter is 4 feet. I need radius on that. So the volume of a sphere is 4/3 pi r cubed. In this particular case, I know the rate of change of the volume is 8 feet cubed per minute, so dv dt is 8 feet cubed per minute. And I know the radius of this is going to be 2 feet. Important to look for those units of measure, and important to know which measurement you have. So then dv dt is going to be 4 pi r squared times dr dt. So you set it up as 8 equals 4 pi times 2 squared times dr dt. When I plug in all those values, and what I ended up with is dr dt is 1 over 2 pi, and it's feet per minute. Or again, as a decimal, it's 0.159. and that would be feet per minute. So, related rates, not the easiest of topics, I'll say that, but you've got to plug away at it. If you plug away at it and you hang in there and you just write down everything you're going to know, draw the relationship between the variables, take your time, ask lots of questions, you'll get it, but it does take a little bit of work. See you in class, and I'll clarify all this as we get there.